Good afternoon, students, counselors, and other friends. Welcome to this session on counseling for our BDP course MTE06, Abstract Algebra. For those who may not recall, I am talking about the course, the blocks of which are, as you see just now, on the screen. So, let me begin by giving a brief overview about groups and group theory. You see, why are groups important? Why do we study them? And what is it about groups that we start off, in fact, in the course with groups? The group, a group, as you see it now, is actually an axiomatic approach, axiomatically defined what was originally really symmetries and the set of symmetries and the way operations on it really came up. So, the origin lies in that, in what was then in fact called substitutions, and the theory really evolved from there. And as you go along, we will see why these substitutions or symmetries really form the underpinning of groups. Now, you may think groups are just for groups, for mathematics, but they are important and useful in so many walks of life and walks of study. For example, in physics, you study the laws of conservation, you need these to study them. You need these in chemistry to study basics like molecules and atoms. You need them in psychology, you need them in ecology to study different aspects, particularly where actions come in. Now, the strength of this is really structure. You study broadly the strength of the axiomatic approach, which really came in with Emmy Noether in the early 20th century and so on, is you're studying them axiomatically. You study one group, the properties you have of one group work for any group then. If you study finite groups, say any group of order 30, then whenever you get a group of order 30, you know it has to satisfy these properties. So, that is the strength of studying axiomatically, so that you kind of in one go are studying infinitely many objects. That is the beauty of abstract algebra, be it groups, be it rings, be it fields. So, let me now just give you a brief overview of what the aims and objectives of this course are. Algebra basically is the foundation of all mathematical thinking. Understanding and using algebra is what gives you strength for doing any mathematics. Why? Because it helps you develop the processes, the absolutely essential processes of mathematical thinking. The ability to generalize and particularize. What does this mean? This is actually inductive and deductive thinking, but in the context of mathematics. You see several situations and you start getting a feel for it and you say, okay, in general, is this true or not? On the other hand, if you've deduced a result, for example, every cyclic group is abelian, then you know that you take any particular cyclic group, you know it will be abelian, and you can work with that. So, the ability to generalize and particularize, the quality of logic and the flow of logic required in proving or disproving a statement. This is what gets built up when you are doing this. And of course, the strength of the precision of the symbols used and used logically. That is mathematics as a language. The underpinning is what you learn in algebra. Mathematics is a language like any other language, and now when you start using symbols and you see the flow, the grammar of the flow in the language, that is algebra. So, you have seen that while doing the course, but our problem is that that comfort that you need to develop in the use of symbols, the logical connectives and the other parts requires some more exposure and using of it. So, the next aim is the content, understanding the structures that we are bringing you to, and these are broad structures. As I said, it is a categorical approach: groups, rings, fields. The course, as you know, is a 4-credit course, which means roughly a semester course. It takes 120 hours of your study time totally on an average. That is what we expect, of which actually about 90 hours on studying the units and about 30 hours for doing the assignments, going to the counseling sessions, seeing the audios and videos that are related. So, that is how we kind of calculate it, and then of course, you know the term end exams are June and December of every year. So, the assignment that you need to give, it comes, we place it on the site for you to download every January, और आपको उसी January से लेके December तक के दौरान आप उसको कभी भी जमा कर सकते हैं. You must study first. पहले आप किताबों को तो देखिए और फिर आप आगे असाइनमेंट कीजिए. हाँ, और असाइनमेंट देने के बाद ही आप इम्तिहान के लिए भर सकते हैं. The term and examination that you file for, that you pay for, you can only do after submitting your assignment. Please remember that. But let us come to the blocks first. Let me remind you what the blocks are for. There are 4 blocks. The first one is on elementary group theory, which of course, as we start, is basics about sets, operations, groups, what a group is, and several examples of groups which you are familiar with, like the integers, integers modulo n, complex numbers, the permutations, and the properties of groups. Then we come to subgroups in the next unit and the properties of subgroups. Now, which subset, when is a subset a subgroup, what are the criteria for that? A couple of criteria we have discussed in the course. A good example of a subgroup, a very crucial example, as you will find later, apart from several other examples that we have done in the course, is the center of a group, G, ZG, the center of G. I will come to that later also, particularly in block 2, it takes on a greater role. Then we talk briefly about the generating set of a group, but in the context of leading you to a cyclic subgroup. And then the last unit is really looking at the order of a group, a finite group that we take, which has a certain order, and the Lagrange's theorem in that context. Now, to do Lagrange's theorem, of course, you need to talk about cosets. So, we have discussed that too, and Lagrange's theorem, as you know, is about the order of a subgroup of a finite group dividing the order of the group. Please remember, it does not necessarily work the other way, but in some cases it does, which we have talked about in the block, particularly a cyclic group. In that case, it works the other way too. Okay. Now, we look at the other block, which is carrying on in group theory, normal subgroup, and then very naturally leading from normal subgroups to quotient groups. Quotient groups, group homomorphisms, isomorphisms, automorphisms come into play, and the very important fundamental theorem of homomorphism for groups. As you remember, it also for rings, later you take it on for rings, and in an earlier course you have done it for vector spaces for linear algebra, in the course on linear algebra, you have done it for linear transformations. Now, there are two other isomorphism theorems that actually follow from FTH, and that is why this one is called the fundamental theorem. Then we go on to talk about permutation groups, properties of symmetric group and the alternating group. We talk about why and how the symmetric group is the, in a sense, mother of all groups. Cayley's theorem tells us that. Then the direct product of groups, Silo theorems, which we have not proved, of course, but we have used. These are very crucial theorems developed by the Scandinavian mathematician Ludwig van Silo. Then, just to give you a feel, we have particularly focused on the structures of certain groups of orders 1 to 10. So, in fact, this is what we really talk about, and in fact, when we are talking about structure, we are talking about algebraic, what it looks like algebraically and how it behaves algebraically, a group. Here, I will just bring your attention to isomorphisms. When are two objects isomorphic? When are two algebraic objects isomorphic? When are two groups isomorphic? When are two rings isomorphic? They are isomorphic when they have the same structure and the same properties. For example, if one is a cyclic group and another is not cyclic, they can't be isomorphic. If one is abelian, it cannot be isomorphic to a non-abelian, right? Okay, so let me continue to an overview. Elementary ring theory similarly we come to, and here, just as in groups, we talk about rings and their properties. Now, Z you were introduced to as a group, as you were to Zn. Now, you see there is another operation that comes into play, and with respect to these two operations that are on the set concerned, the non-empty set, let me stress non-empty here, it becomes a ring. Similarly, the reals, the complex and the set of matrices n cross n or m cross n over reals. Here there is one thing I would like to say about our course. Groups we have spoken of a lot about, be it abelian, be it non-abelian, be it whatever, but about rings we have largely adhered to commutative rings only, though we have given you, as you can see, examples of non-commutative. For example, MNR is non-commutative, but largely we have discussed commutative rings. This slide we see the FTH for rings, and as in the case of groups, the same thing for the other two isomorphism theorems here too. And the final block covers certain kinds of rings, which are integral domains and fields. Now, something akin to normal subgroups are prime ideals, are ideals. So, earlier we have spoken of ideals in the block 3, but here we look at particular kinds of ideals, which are prime and maximal. Then we go on to quotient fields. Now, quotient groups, quotient rings, quotient fields. Quotient fields are actually easier for some people, maybe because you have dealt with it in the context of Z and Q, but these are normally areas that you are not very comfortable with, as I have found. So, I will spend a bit of time on this a little later. We go back to seeing what block 4 is about. We talk about polynomial rings and the division algorithm. You have studied division algorithm in the context of Z, which is a PID. Here we look at it as a field Kx, polynomials over a field k in one variable, that is also a PID, and we look at the division algorithm there, the roots of a polynomial with multiplicities, and particularly we look at Euclidean domains, PIDs and UFDs and the interrelationship. Every Euclidean domain is a PID, is a UFD, etc. The fundamental theorem of algebra, which is crucial, That's why it's called the fundamental theorem. It's about roots. We have mentioned that also in the course. Then in the last unit, we really talk about irreducible elements, units, and the Eisenstein's criterion, which some of you turn into Einstein's criterion and so on, different versions of it. Eisenstein was a mathematician on his own. We go on to field extensions, the prime field and the characteristic of a field. ये slide में देखिए, at the end of the slide मेरा email ID दिया है pksinclair@ignou.ac.in. प्लीज़ अपने सवाल लिखिए इस ID को. फीडबैक इस सेशन पे आप भेजिएगा ज़रूर, तभी बात हम आगे कर सकते हैं. शुक्रिया. थैंक यू वेरी मच एंड जय हिंद.